Hi, good evening. Let's start something where we left and now we start again. Okay, so it is. Let's define the generalized coordinates. Generalized coordinates arrangement configuration space mechanical system simplifying analysis incorporating constraints. Definition generalized coordinates qi equal to the 1 to the n and n degree freedom. Uniquely specifies system positions independent Cartesian choices represents length, angles, other parameters unlike the fixed x, y, z and number equal degree freedom after the constraints. Advantages handle the constraints automatically, pendulum angle theta enforces fixed length, avoiding the tension calculation. Enable Lagrangian L equal to the T minus V terms qi dot yielding Euler Lagrange length Lagrange equation without constant forces. Exploit the symmetries. L is the independent and Qj and Pj equal to dl divided by the dqj dot is conserved. So single pendulum theta 1 degree of the freedom and double pendulum theta 1 theta 2 2 degree of the freedom spherical pendulum theta 1 theta phi 2 degree of the freedom on a sphere. Now it is Lagrangian Hamilton formalism. Lagrangian Hamilton formalism equation of the motion. Lagrangian Hamiltonian formalizes reformulate classical mechanics. Energy based function derive equation motion variational principles. Lagrangian formalism. Lagrangian L equal to T minus V depends generalized coordinates qi velocities qi dot time equation motion follow Euler Lagrange equation d by dt and bracket 1 dl by dqi dot and minus dl by dqi and equal to 0. This yields the second order differential equation equivalent Newton's law automatically handling the constants. Hamiltonian formalism and define generalized moments pi equal to dl by dqi dot Legendre transform Hamiltonian h equal to summation I and pi qi dot minus l Laplace and rho q rho p and typically h equal to t plus v. Now Hamiltonian's equations first order qi dot equal to dh divided by the dpi. Now the pi dot minus dh by dq and fits the space q and p emphasizes symmetry and conservations. Example H constant for time independent system comparison. Lagrangian uses q and comma q dot. Hamiltonian uses qp. Both yield identical trajectories, but Hamiltonian suits quantization, statistical, mechanical better. Conservation laws and cyclic coordinates. Next. Cyclic coordinates in Lagrangian mechanics lead directly conservation's law via the Noether theorem or Euler's Lagrange equation. Cyclic coordinates a generalized coordinates qk cyclic ignorable if the Lagrangian L does not explicitly depend on the qk only on the qk dot and other variables dl by dq k and equal to the 0 from Euler's Lagrange and d by dt bracket 1 dl by dq k dot equal to 0. So conjugate momentum pk dl by dqk dot and is conserved. Conservation's laws, this embodies Noether's theorem, cyclic qk signal symmetry invariance under the qk tends to the qk plus delta. Now conserving the pk and time independent L cyclic T energy H conserved transit translational invariance cyclic X and linear momentum conserved rotational invariance cyclic phi angular momentum conserved. Example free particle L equal to the 1 by 2 mx dot square and cyclic X 10 to the px and mx dot equal constant. Central force in the spherical coordinates cyclic phi and 10 to the p5 equal to the m r square phi dot angular momentum constant. Periodic motion, small oscillations, and normal modes. Periodic motion repeats regular interval with small oscillations around the equilibrium approximated as the simple harmonic motion SHM. Normal modes describes collective oscillations in coupled system at a specific frequency. Small oscillations near stable equilibrium expand potential VQ equal to V naught plus 1 by 2 summation Kij Nij, where Ni equal to the Qi minus Qi equivalent and Lagrangian Yeltsin matrix equations. Now m neta double dot plus k neta equal to the 0, and therefore neta double dot plus omega square neta equal to the 0. After diagonalization with the omega square from eigenvalues of the m ki power minus 1k, normal modes will be the solutions are the neta it equal to the ai cos bracket 1 omega k T and plus phi k, where each mode k has frequency omega k and all the masses oscillate at that single omega k with a fixed phase ratio, mode shape uncoupled, and modes allows superposition for the general motion. Example coupled pendulum symmetric mode omega 1 equal to under root g by L, antisymmetric omega 2 greater than the 1 omega 1 molecules vibrational normal mode observed in the IR spectra. Let's derive the small approximation for the nonlinear potential. A small oscillations approximation for a nonlinear potential expands potential energy around a stable equilibrium using a Taylor series retaining only quadratic term. Taylor expansion equilibrium considers system potential VQ have the stable minimum at the Q equal to Q naught and where the dV by the dqi and the mod Q naught equal to the 0. Define the displacement neta equal to the Qi minus Q naught bracket 1 I, the Taylor expansion gives the V bracket 1 Q equal to the V Q naught plus 1 by 2 summation I j and del square V by dqi plus dqj and Q naught and neta j plus order neta ki power 3 small neta neglect higher order V equal to 1 by 2 neta ki power t into A into neta with aij equal to the d square V by dqj and the Q naught symmetric and positive definite. Kinetic energy approximations. Kinetic energy T equal to 1 by 2 summation ij and m ij q bracket q and qi dot qj dot equal to the 1 by 2 neta dot t and m neta dot evaluating mass matrix m ij at the q naught and constant for small theta, Lagrangian Laplace equal to t minus v. Here's the equation m into the neta double dot plus a neta equal to the 0. Normal mode solutions diagonalized by the orthogonal transformation to the normal coordinates zeta k t equal to the 1 by 2 summation zeta k square and v equal to the 1 by 2 summation omega k square zeta k square with the zeta k double dot plus omega k square zeta k equal to the 0 SHM at the frequency omega k equal to the root lambda k eigenvalues of the m minus 1 into the a general motion superposition these decoupled oscillators. Now let's now the next topic will be special theory of the relativity, Lorentz transformation, relativistic kinematics, and mass energy equivalence. Special relativity unifies space-time into the space-time with the Lorentz transformations relating coordinates between the inertial frames moving at the constant velocity leading to the relativistic kinematics and the mass energy equivalence equal to the mc square Lorentz transformation for the frames S and S dash with the S dash moving at the velocity v along the x-axis relative to the s the transformations are x dash equal to the lambda bracket 1 x minus vt a comma t dash equal to the gamma t dash equal to the gamma bracket 1 t minus vx divided by the c square comma y dash equal to the y and z dash equal to the z where lambda equal to the 1 divided by the under root 1 minus v square by the c square inverse swap prime v tends to the minus v this preserve the space time interval s square equal to the c square t square minus x square minus y square minus z square ensures a light speed c invariance. Now relativistic kinematics. Now the time dilation proper time tau and frame clock relates to the coordinate time delta t equal to the gamma into the delta tau length contraction proper length and the L naught rest of frame measures the L equal to the L naught by the gamma and along the motion but velocity addition for object velocity u x equal in the s in a s dash equal to it is the ux dash equal to ux minus v and divided by the 1 minus uvx divided by the c square preventing the superluminal speed's momentum p equal to the gamma mv with the relativistic mass gamma m though invariant mass m preferred so mass energy equivalence work energy theorem in the relativity for the particle accelerating from the rest total energy E equal to the gamma mc square kinetics k equal to the bracket 1 k equal to bracket 1 gamma minus 1 mc square rest energy is the E naught equal to the mc square where when the v equal to the 0 total E square equal to the p square c square plus m square c to the power 4 conservation holds for the E comma p. Let's derive the relativistic velocity addition. Derive the relativistic velocity addition formula and using the boosts. Now, next topic will be the electromagnetic theory. Special theory, relativity, Lorentz transformation, relativity, kinematics, and mass energy equivalence. It will, I think, it is the term. Okay, not derive. Let's derive the relativistic velocity addition formula using the boost. Relativistic velocity addition follow how Lorentz boost transforms space and time between inertial frames using a boost along the x-axis and gives the standard 1D formula. Set up the Lorentz boost. Consider frame S and S dash where S dash move with the speed v and plus x directions relative to the s. The boost from s to s dash is the x dash equal to the gamma bracket 1 x minus vt, where comma t dash equal to the gamma bracket 1 t minus vx divided by the c square, comma y dash equal to the y and z dash equal to the z, with the gamma equal to the 1 and by under root 1 minus v square by the c cube, c square. So an object moves in a s with the velocity component ux equal to the dx by dt, uy equal to the dy by dt, and uz equal to the dz by dt. Derive the 1D addition law. Take the differential of the boost dx dash equal to the gamma bracket 1 dx minus v dt and comma dt dash equal to the gamma bracket 1 dt minus v by c square dx. The x component of the velocity in s dash is the ux dash. Ux dash equal to the dx dash by dt dash equal to the gamma bracket 1 dx minus v dt divided by the gamma bracket 1 dt minus v by c square dx equal to the dx minus v dt divided by the dt minus v by c square dx. To divide the numerator and denominator by the dt using the dx by the dt equal to the ux. So therefore ux dash equal to the ux minus v divided by the 1 minus v into the ux divided by the c square. This is the relativistic velocity addition formula along boost direction velocity object s dash given velocity ux in s and frame speed v, including the transverse components for the completeness using the same boost uy dash equal to the dy dash divided by the dt dash equal to the dy divided by the gamma bracket 1 dt minus v into the dx divided by the c square equal to the uy equal to the uy divided by the gamma bracket 1 1 minus v into the ux divided by v into the ux divided by the c square. And similarly uz dash u z dash equal to the uz divided by uz divided by the uz divided by the gamma bracket 1 1 minus v into the 1 minus v into the ux divided by the c square. They just shows how single Lorentz boost pure boost along the x produces the full 3D 3D relativistic velocity transformations. Electrostatic Gauss law and its applications. Gauss law states that the electric flux electric flux through any closed surface equals the enclosed charge divided by the permittivity of the free space. Now closed integral E into the dA now equal to q enclosure divided by the epsilon naught derivation from the Coulomb's law for a point charge q at the origin equal to the qr divided by the 4 pi epsilon naught r cube and flux through a sphere of the radius r and closed integral E dot dA equal to the E into the 4 pi r square equal to the q by epsilon naught. By the superposition, this holds for any charge distribution arbitrary Gaussian surface. Symmetry not required for the validity, only for application. Infinite line charge. For the line charge density lambda, use the cylindrical Gaussian surface, radius r, length L, flux E into the 2 pi RL equal to the lambda L divided by the epsilon naught. So E equal to the lambda divided by the 2 pi epsilon naught r and filled filled radial and independent of the position along the line. Infinite plane sheet. Now the supercharged surface charge sigma Gaussian pillbox piercing sheet flux E into the 2a E into 2a equal to the sigma a divided by the epsilon naught. So E equal to the sigma divided by the 2 epsilon naught perpendicular same on both the side. Spherical cell uniform surface charge q on the radius r outside bracket 1 r greater than the r spherical Gaussian surface gives the spherical Gaussian surface E equal to the q divided by the 4 pi epsilon naught 4 pi epsilon naught r square point charge like inside bracket 1 r less than capital R q enclosed equal to the 0. So equal to the 0 for the solid uniform sphere inside the E equal to the qr divided by the 4 pi epsilon naught r cube. Now let's apply the Gauss law to a long charged wire. Gauss law simplified finding the electric field infinitely long straight wire with a uniform linear charge density lambda exploiting the cylindrical symmetry. Gaussian surface choice. Now select a coaxial cylindrical Gaussian surface radius r length L enclosing the charge and the Q enclosure lambda L flux through the curved side and closed integral E dot dA equal to the E to E dot 2 pi RL filled radial and the constant magnitude by the symmetry and ends the contribute 0 E perpendicular to the dA. Apply the Gauss law. Gauss law gives the E dot 2 pi RL and equal to lambda L divided by epsilon naught and cancel L and equal to the lambda divided by the 2 pi epsilon naught R. Directions radially outward, lambda greater than the 0. Field characteristics. Field falls as the 1 by the r bracket 1, unlike 1 by the r square for the point charge, independent of the position along the wire due to the infinity assumptions valid for valid for from ends. Our next topic deals Laplace and Poisson's equations boundary value problem. So let's start. Laplace equations Laplace square phi equal to 0 governs the electrostatic potential charge free region, while the Poisson's equations Laplace square phi equal to the minus rho by the epsilon naught includes the charge density. Derivation from the Gauss law. Now from Laplace dot E equal to the rho divided by the epsilon naught and E equal to the minus Laplace phi bracket 1 E rotational field, substitute Laplace dot bracket 1 minus Laplace phi equal to the rho divided by the epsilon naught. So Laplace square phi equal to the minus rho divided by the epsilon naught bracket 1 Poisson, that is a charge free rho equal to the 0 else Laplace, both are elliptic partial differential equation requiring the boundary condition for the uniqueness. The boundary value problems, Dirichlet's specify the phi on the boundary. Example, conductor potential. Newman specify the normal derivative d phi by the dn, and example, surface charge sigma equal to the minus epsilon naught d phi divided by the del d phi by the dn. And uniqueness theorem solution unique up to the constant for the Dirichlet and for the Newman if the closed integral d phi by the dn into the dA equal to the 0. Gauss consistency solutions method, separation of the variables in the Cartesian and the spherical or the cylindrical coordinates yield the series solutions. Example, Legendre polynomial for the spheres. Superpositions applies due to the linearity. And example potential between the concentric spheres solved by the spherical harmonics. Let's use the Green's theorem to solve the Poisson's boundary problems. So Green's functions turn Poisson boundary value problems into the integral formulas for the solution, separating the geometry in the Green functions from the sources in the simple integral. Green's functions for the Poisson's equation for the Poisson's equations Laplace square phi r equal to the minus fr. In the domain D with the given boundary conditions, define the green functions g bracket 1 r comma r dash as the solution of the Laplace square g bracket 1 r comma r dash equal to the minus del bracket 1 r minus r dash. In D with the same homogeneous boundary condition phi integral solution with the four sources. Once the g is known, the solution of the Poisson's problem with the source f and Dirichlet data phi by the delta d equal to the g can be written using the Green's identities as phi r equal to the closed integral d g bracket 1 r comma r dash and f r dash dv dash plus integral closed integral dd and bracket 1 g r dash and dg by the day d and dash bracket 1 r comma r dash and minus g bracket 1 r comma r dash and d phi by d n dash and bracket 1 r dash and bracket 1 d s dash. So where the d by d n dash outward normal derivative at r dash. So for the pure Dirichlet's problem, only phi equal to the g specified on the delta d on one use as the Green's function vanishes on the boundary. Then the term with the d phi by dn dash drop out and giving the phi r equal to the closed integral d and g bracket 1 r comma r dash and f r dash d v dash plus closed integral d dd g r dash and del g by del n bracket 1 r comma r dash and ds dash. So now electrostatic interpretation. In electrostatic, Fr equal to the Pr rho r and divided by the epsilon naught. So suitable free space Green's functions g bracket 1 r comma r dash equal to the 1 divided by the 4 pi bracket mod r minus r dash yields the familiar Coulomb's integral phi r equal to the 1 by 4 pi epsilon naught integral rho r dash divided by the mod r minus r dash dv dash for an unbounded domain. For the boundary domain, G is a modified example by the images satisfy the boundary, but the same integral structure solves the Poisson's boundary value problem. Now let's derive the integral solution for the Poisson's equations with the function. Green functions. So for the Poisson's equations, Green's identity plus defining the equation for the Green's function give an integral formula solution in terms of the sources and boundary data. Set up Poisson's and Green's function. Now consider the Poisson's equation region D and Laplace square phi r equal to the minus fr with the boundary delta D. Define the Green's function g bracket 1 r comma r dash. Now the Laplace r squared and g bracket r comma r dash and minus delta r minus r dash. Now r dash now g dot d and let the g satisfy homogeneous boundary condition compatible with the boundary condition and phi and g equal to the 0 and delta d Dirichlet's problem. Use the Green's second identity to two functions. Now the mu u r dash comma v r dash in the d and integral d. Now u v dash square v minus v and Laplace square dash u and dv dash and close integral delta d and bracket 1 mu into dv by dn dash minus v into du by dn dash and ds dash. Choose u r dash equal to the phi r dash and v r dash equal to g r comma r dash. So note Laplace dash r square phi r dash minus equal to the minus f r dash and further Laplace dash square g r comma r dash minus delta r minus r dash. So substitute into the Green's identity integral d mod bracket 1 phi r dash minus delta minus g r comma r dash minus bracket 1 minus f r dash dv dash equal to close integral dd and delta g and by the d del n dash minus g d phi by dn dash and ds dash. Volume integral simplified using the delta functions minus phi r plus integral d g bracket 1 r comma r dash. Now f r dash dv dash equal to the closed integral delta d and bracket 1 phi r dash dg by the dn dash bracket 1 r comma r dash minus g bracket 1 r comma r dash d phi by the dn dash and r dash bracket 1 ds dash. Rearrange and solve for the phi r. So phi r equal to the integral d g bracket 1 r comma r dash. Now f r dash dv minus closed integral dd and bracket 1 phi r dash dg by the dn dash bracket 1 r comma r dash and minus g bracket 1 r comma r dash d phi by dn dash r dash ds dash. So integral solution, common boundary types, Dirichlet's problem, bracket 1 phi equal to the g given on the dd. Choose the g such that the g equal to 0, delta d and d phi dz by the dn dash remains term g d phi by dn dash drops phi r equal to the integral d g bracket 1 r comma r dash and f r dash dv minus closed integral dd and gr dash dg by the dn dash bracket 1 r comma r dash ds dash. The Newman problem d phi by the dn equal to the h on the dd. Choose the g with the dz by the dn dash and equal to the 0 dd and then boundary term simplified one involving the gh and in electrostatic f r equal to the pr rho r divided by the epsilon naught for the free space g bracket 1 r comma r dash equal to the 1 divided by the 4 pi mod r minus r dash giving familiar Coulomb integral special Green's function solution Poisson's equations. Now next topic will be what? Next topic deals with the magnetostatics, Biot-Savart law, Ampere theorems, electromagnetic inductions. So Biot-Savart law gives the magnetic field from steady current analogous to the Coulomb's law. Analogous to Coulomb's law for the charging charges. Ampere theorem relates the magnetic circulation to enclose the current. Electromagnetic induction describes the changing fields inducing the EMF. Biot-Savart law. For the current element I dl at position r dash, field R is the dBr and equal to the mu naught divided by the 4 pi and I into dl into r minus r dash divided by the mod r minus r dash cube and total b equal to the integral dv derive experimentally consistent with the Maxwell's equations in the magnetostatics. Ampere's theorem closed integral b dot ds applied with the Amperian loops exploiting symmetry. Example: straight wire b equal to the mu naught I divided by the 2 pi r solenoid b equal to the mu naught n I follows from Laplace cross b equal to the mu naught j. Now electromagnetic inductions. Now Faraday's law induce the EMF zeta equal to the minus d phi b divided by dt phi b equal to the integral b into dA. Lenz law gives the sign opposes the chain for moving conductor or B motional EMF zeta equal to the closed integral V into V cross B dot dl. Next will be the Maxwell equations in the free space and linear isotropic media. So Maxwell equations unify electricity, magnetism, and optics, describing electromagnetic fields in the vacuum free space, no charges, currents, linear isotropic media with a uniform permittivity zeta and permeability mu. So free space is the vacuum, and in free space bracket when rho equal to the 0 and j equal to the 0, epsilon not equal to epsilon not equal to the epsilon naught mu equal to mu naught and Laplace dot E equal to the 0 and Laplace dot B equal to the 0. Laplace cross E equal to the minus del B by del T. So Laplace cross B equal to the mu naught epsilon naught dE by the dt equal to the 1 by C square dE by dt. So where the C equal to the 1 divided by the under root mu naught epsilon naught is the speed of the light. This predicts the transverse EM waves and propagating at the sea. Linear isotropic media in the media with a constant scalar zeta and mu, no free charges or the currents. Laplace dot d equal to the 0, Laplace dot the b equal to the 0, Laplace cross e equal to the minus dv by the dt, Laplace cross h equal to the dd by the dt, where the d equal to the zeta into the e, and wave speed mu equal to the 1 by the root mu into epsilon naught. Refractive index equal to the n refractive index equal to the refractive index n equal to the c divide by the v. So key implication, taking the curl Faraday's laws and substituting the Ampere's Maxwell Yields wave equation, Laplace square e equal to the 1 by the c square del square e by the and dt square free space, confirming light electromagnetic waves media support the waves reduced speeds. Next topic will be what? So boundary conditions on the field. Boundary conditions on the fields at the interfaces. Electromagnetic boundary conditions at the interfaces between the media, dielectric conductors arises from the Maxwell equation applied by the pillbox or the loop integrals across the boundary. Normal components. The normal component B is continuous B1 perpendicular equal to the B2 perpendicular from the Laplace dot B equal to the 0 bracket 1, no magnetic monopole, no monopole. D. For the D, the discontinuity equals surface charge D2 perpendicular minus D1 perpendicular. So equal to the sigma F, and where sigma F is the free surface charge density, and bracket 1 0 without free charges. Tangential E is a continuous E1 parallel equal to the E2 parallel. So from the Faraday's laws, Laplace cross E equal to the minus dv by the dt and loop integral. Tangential yet satisfied H2 parallel equal to the H1 parallel and equal to the kf cross n cap, where the kf is a free surface current from the Ampere's law. Applications at the dielectric interfaces, kf equal to the 0, no sigma f e parallel and d perpendicular, continuous if no free charges for the perfect conductors. E parallel equal to the 0 and B perpendicular equal to the 0. This ensure the field matching for the reflections or the transmission. Example, the Fresnel equations. Let's derive the boundary condition from the Maxwell equation step by step. The boundary conditions at the interfaces follow from applying the Maxwell equation as the integral forms over the infinitesimal pillboxes, loops straddling and the boundary. Normal D and the P. Consider the pillbox with the faces parallel to the interface area, height h im zeta tend to the 0 cos law closed integral dA and q f enclosed and bracket 1 d2 perpendicular minus d1 perpendicular bracket 1 a and equal to the sigma f into the a, and therefore d2 perpendicular minus d1 perpendicular and equal to sigma f. So for the b, closed integral b dot dA equal to the 0, bracket 1, no monopoles, b2 perpendicular minus b1 perpendicular equal to the 0, and sides contribute negligibly as the zeta tends to the 0, tangential E equal to tangential E, rectangular loop parallel to the interface length L along the tangential function height zeta tend to the 0, Faraday closed integral A dot dl equal to the minus d by dt integral B dot dA ends contribute bracket 1 E2 parallel minus E1 parallel. So bracket 1 L flux through the loop tends to the 0, zeta tends to 0, E2 parallel minus E1 parallel, bracket 1 L equal to the 0, E2 parallel and equal to E1 parallel, tangential H. Now same loop for the imperial Maxwell. The closed integral H dot dl equal to the integral bracket 1 jf plus jf plus del d by del t in dot da end gives h2 parallel minus h1 parallel and bracket 1 l. Enclose the current and kf into the l surface current displacement tends to 0. Therefore, h2 parallel minus h1 parallel bracket 1 l equal to the kf into the l, and therefore h2 parallel minus h1 parallel equal to the kf and kf cross n cap. So here the n point from the region 1 to the 2 and summary table component condition physical origin. D perpendicular equal to the d2 minus d1 equal to the sigma f free surface charge. B perpendicular equal to the b2 equal to the b1 no magnetic monopoles. E parallel will be the e2 equal to the e1 and e rotational e, and h parallel equal to the h2 minus h1 equal to the kf cross n cap free surface current. Now next topic will be the scalar and vector potential. Scalar and the vector potential and gauge invariance. Now scalar and the vector potential simplify the Maxwell equations by expressing the fields in the terms of the potential with the gauge invariance allowing non-unique choices that preserve physical observables definitions magnetic definition and electric field combines scalar potential phi and vector potential E equal to the minus Laplace phi and minus del A by del T. This satisfies Faraday's laws automatically. Laplace dot B equal to 0 holds by the constructions. Now Gauss transformations. Potential transform as the A dash equal to the A plus Laplace uh, zeta and phi dash equal to the phi minus dx by dt, where the zeta bracket 1 r comma t arbitrary scalar fields unchained. Laplace cross a dash equal to the Laplace cross a curl or gradient 0, e dash equal to the minus Laplace and bracket 1 phi minus d zeta by dt bracket 1 minus d by dt bracket 1 a plus Laplace zeta equal to the e. Common causes. Now Coulomb Gauss. Now the Laplace dot equal to the 0 simplifies to the Laplace square phi equal to the minus rho by the epsilon naught. Transverse waves for the A. Lorentz Gauss. Laplace dot A plus 1 divided by the c square d phi by dt equal to the 0. yields the wave equations Laplace square phi equal minus 1 by c square d square phi by the dt square equal to the minus rho divided by the epsilon naught. Next topic is electromagnetic waves in the free space. Electromagnetic waves, free space solutions, Maxwell's equations with no charges or currents propagating at the speed light consisting mutually perpendicular electric and magnetic fields. They are the transverse waves where E, B propagation directions are all orthogonal. Wave equation, speed, Maxwell equation, Maxwell equation reduced to the Laplace dot E equal to the 0, Laplace dot B equal to the 0, Laplace cross E equal to the minus dB divided by the dt, and the Laplace cross B, Laplace cross B equal to the mu naught epsilon naught dE by dt, taking the curl of the Faraday's laws using the vectors identity for the Laplace cross bracket 1 Laplace cross E gives the Laplace square E equal to the mu naught epsilon naught d square E by the dt square. Similarly, Laplace square B equal to the mu naught epsilon naught d square B by the dt square. These are the wave equations with the wave speed c equal to the 1 divided by the root mu naught epsilon naught, identifying the light as the electromagnetic wave in the free space. Plane wave structure, monochromatic plane wave solution written as the E bracket 1 R comma T epsilon naught cos bracket 1 K into R minus omega T, and B bracket 1 R comma T equal to the B naught cos bracket 1 K R minus omega T. Maxwell equation imply K into the E naught equal to the 0, K into the B naught equal to 0. So both the fields are the transfers to the direction of the propagation k. They also give the b naught equal to the 1 by the omega into the k cross f psi cross k in k cross e naught. K cross E naught, so E, B, K form the right-handed orthogonal triad with the mod E naught equal to the C, B naught. So energy and polarization. The time average energy density mu equal to the 1 by 2 epsilon naught E square and plus 1 by the 2 mu naught is into the B square, and for the plane wave these contributions are equal. So energy flow by the pointing the vector S equal to the 1 upon the mu naught E cross B in the direction of the K. Now polarization describes the orientation of the E. If the E oscillates along the fixed line, the wave is linearly polarized. If it's a tip trace circle ellipse in a transverse plane, wave circularly and elliptically polarized, all still satisfying the same trace space wave equations. Now, dielectrics and the conductors. Dielectrics are insulating materials that polarizes in electric fields, reducing the effective field inside, while the conductors allows free Conductors allow the free charge movement leading to the surface charges and zero internal fields in the electrostatics. Dielectrics polarization P arises from the aligned dipoles and giving the displacement fields D equal to the zeta E zeta naught E plus P equal to zeta E. Linear isotropic case. F zeta equal to epsilon naught 1 plus zeta e bound charges rho v equal to the minus Laplace dot p surface sigma b equal to the p dot neta case Gauss per ampere law use the free charges. Now Laplace dot d equal to the rho f. So conductors electrostatic. Now the inside the perfect conductors equal to zero charge rearrange instantly, so the B static to excess charge resides on the surface sigma equal to epsilon naught E perpendicular cavities without the charge have the zero integral field. In the AC fields, a skin effect confines current to surface boundaries. Dielectric tangential E normal D continuous no free charge conductor dielectric tangential equal to zero normal D equal to sigma F. Just outside methods of images solves the conductor problems by mirroring charges. Now, next topic will be the reflection, refraction, polarization, Fresnel's law, interference, coherence, and diffraction. So, reflection, refractions, electromagnetic waves, interfaces follow Snell's law, Fresnel equations with polarization affecting the amplitude, interference. Interference requires the coherence, while the diffractions arises from the wave nature around the obstacles. Reflections and refractions. Incident plane wave at the dielectric interface obeys the Snell's law n1 sine theta 1 equal to n2 sine theta 2 sine theta t, where the n equal to the under root zeta r mu r reflected angle equals the incident, and Fresnel equation gives the amplitude coefficient for S polarization bracket 1 E perpendicular plane of incidence Rs equal to the n1 cos theta I minus n2 cos theta t divided by the n1 cos theta 1 plus n2 cos theta t. For p polarization, E parallel to the plane Rp equal to the n2 cos theta I minus n cos theta t divided by the n cos theta I plus n1 cos theta t at the Brewster angle tan theta b equal to the n2 by the n1 and rp equal to the 0, no p reflection. Polarization. Waves are linearly polarized if E oscillates in the fixed direction. Circularly if the tip traces circles reflection and partially polarizes the unpolarized lights more as reflected. Transmitted wave polarization preserved in the linear case. Interference and coherence. Superposition of the waves yields interference constructive if the path difference is the m lambda. Destructive if the m bracket 1 m plus 1 by 2 lambda requires the temporal or spatial coherence bracket 1 fixed phase relation sources like the lasers coherent sunlight and the incoherent diffractions waves bands around the edges or through apertures example single slit pattern minima at the sine theta equal to the m lambda divided by the a Huygens-Fresnel principle. Each point act as a source. Interference forms patterns, limits resolutions. Microscope theta lambda by d. Now, next topic will be the dynamics of the charged particle in the static and uniform electromagnetic field. Dynamics charged particles in the static and uniform electromagnetic fields follows from the Lorentz force law and leads to the simple standard trajectories, lines, circles, helix, drifts. Basic equation of the motion: a particle with a charge q, mass m, electric field E, magnetic field B obeys the. Therefore, m into dv divided by dt equal to the q bracket 1 E plus v cross b. With the E, comma b taken constant in space and time, only electric field uniform acceleration if the b equal to the 0 and E is the uniform, then m into dv by dt equal to the q e, and therefore vt equal to the v naught and plus q e t by the n. So motion is uniformly accelerated along the e parabolic trajectory in the space. Only magnetic field circular L helical motion equal to 0. B is the uniform and m dot dv by the dt qv cross b. The magnetic force is always perpendicular to v, so it does no work and speed mod v is a constant. Decompose v equal to v parallel plus v perpendicular, where v parallel and parallel to the magnetic field and v perpendicular for the perpendicular to the magnetic field. V parallel is unaffected straight line motion along the b. V perpendicular executes the uniform circular motion with, and cyclotron Larmor frequency omega c equal to the mod q b by m, radius rl, and mv perpendicular by the mod q b. Thus the trajectory is a helix around the field lines if the v parallel equal to the 0. It is a circle. Cross E and B, drift and helix. Take the E and B, both the uniform, with the E perpendicular to the B, the Lorentz force. Therefore, m dot dv by dt equal to the qe plus qv cross b. The exact solution can be written as the superposition of a uniform drift with the velocity. So drift velocity equal to the E cross B divided by the B square independent of the Q and M, a circular or helical motion about the magnetic field lines as in the pure B case at the cyclotron frequency. In a framing, in framing, in a frame moving with a VD, the electric field is transformed away and the motion reduces to the pure cyclotron motion. In the lab frame, this appears as a helix whose guiding center drifts with the VD. A special case if the parallel E and the B. If the E parallel to the B, then along the B uniform acceleration m dv parallel upon the dt and qe parallel perpendicular components if any is still and rotates omega c. The trajectory is the helix whose pitch with the time as the particle accelerates along the field. Let's finish the chapter electromagnetic. Electromagnetic theory. Now, next topic deals the quantum mechanics. Quantum mechanics. Interesting one. So let's first topic deal with the wave particle duality. Wave particle duality states quantum entities, photons, electrons exhibit both wave-like and particle-like the properties depending on the experiment. Historical development. Okay, light shows wave behavior, interference, diffractions. Young 1801 particle-like photoelectric effect. Einstein's 1905 equal to h mu. De Broglie 1924 hypothesized matter wavelength lambda equal to h by p, H Planck constant. Davison, Germer, and 1927 confirmed electron diffraction. Key experiments: double slit, single particles create the interference over the time, implying wave nature detection shows the particle hits. Photoelectric effect: light ejects electrons with energy threshold and particle like the quanta and Compton scattering. X-rays scatter of electron with wavelength shift delta lambda equal to the h by the mcc bracket 1 minus cos theta and confirming the photon momentum. Implication: duality is the complementary board web particle aspect mutually exclusive in one step. Heisenberg uncertainty delta x into delta p greater than equal to the h divided by 2 links the positions particle and the momentum or wavelength wave underpins quantum mechanics Schrodinger equations. How does the double slit experiment demonstrate the wave behavior? Double slit experiment demonstrate wave behavior through the formation interference pattern screen and arises solely from the superposition waves passing through both the slits. Now experimental setup: monochromatic light passes through the two narrow closely spaced slits onto a distant screen. Each slit acts as a coherent wave source and producing the cylindrical wavefront that overlap beyond the slits. Interference pattern formation: waves from the slit 1 and slit 2 travel different the path length to the point P on the screen. Constructive interference occurs when the path difference delta equal to the d sine theta equal to the m lambda m integer yielding the bright fringes. Destructive interference when the delta equal to the m plus 1 by 2 lambda yielding the dark fringes. Fringe spacing delta y equal to the lambda L by d, L equal to the slit screen distance. Key evidence of the waves. Single slit shows the diffractions spreading, but double slit produces the multi-fringe interference, impossible for the particles which would cluster at the two spots, even with a low intensity, one photon at the time, and pattern built statistically, implying each photon interferes with itself by both the paths. Quantum extension: identical pattern with electrons confirms matter waves. De Broglie lambda equal to h by p, embodying the wave particle duality and wave interference build the pattern and particle detection at the screen. Now let the Schrodinger equation time dependent and time independent. Now, Schrodinger equation time dependent and time independent. Schrodinger equation governs the evolutions of the quantum wave functions zeta equal to the r comma t analogous to the Newton's laws in the classical mechanics. Time dependent forms for the single particle potential v bracket 1 r comma t I h d zeta by d zeta by dt equal to the minus h square divided by 2m Laplace square phi and zeta and plus v by the v zeta equal to h cap zeta. where H is the Hamiltonian operator total energy. This partial differential equation predicts how the zeta changes over the time with the mod of the zeta square giving the probability density solution. Solutions are the superposition energy eigenstates time independent form. Assume the stationary states zeta equal to the r comma t equal to the zeta r e की power minus I into e t divided by the h. Substitute into the time dependent equation, time independent v. Now the h cap phi zeta r equal to the e and zeta r. So yielding ordinary differential eigenvalue problem for the bound state for the bound states and discrete an example infinite well has the zeta n x equal to the under root 2 divided by the a sine bracket 1 n pi x divided by the a comma en equal to the n square pi square h square by the 2 ma square. Application: time dependent solve the dynamics. Example: the tunneling. Time independent find spectra. Example: hydrogen atom. Linearity allows the superposition measurement collapses to the eigenstates. Eigenvalue problem, particle in a box and harmonic oscillators. No eigenvalue problems, quantum mechanics arise time independent Schrodinger equation H cap zeta and E cap E zeta and discrete energy En and wave function zeta n eigenvalues eigenfunctions Hamiltonian particle in box infinite square well and v equal to the 0 less than x less than the a and v equal to infinity elsewhere. Solution: now the phi zeta n x and equal to under root 2 divided by the a sine bracket 1 n pi x divided by the a and a comma e n equal to the n square pi square and the h square divided by the 2 m a square n equal to the 1 2 and wave function vanishes at the boundary energies quantized 0.E1 greater than 0 harmonic oscillators potential Vx equal to the 1 by 2 m omega square x square eigenfunctions zeta and x and equal to the 1 by the root 2 ki power n n factorial bracket 1 m omega divided by the pi h ki power 1 by 4 and into h n zeta e ki power minus zeta square by the 2 zeta equal to the under root m omega divided by the h x and hn equal to the Hermite polynomials. Energies En equal to the h omega bracket 1 n plus 1 by 2 n equal to the 0 1 equally spaced levels. Hydrogen atom 3D. Now the central potential Vr equal to the minus E square divided by the 4 pi epsilon naught r. Separation in spherical coordinates yields the radial RNL r angular YLM and theta phi spherical harmonics. Energies depend only on the principal quantum number. En equal to the minus 13.6 ev divided by the n square n 1 2 and degeneracy n square from l equal to 0 to the n minus 1 m equal to minus l to the l and now, next topic will be tunneling through a barrier. Tunneling through a barrier. So quantum tunneling, when quantum particle crosses classical forbidden barrier because it is a wave function penetrate extend beyond the barrier. Basic step and classical contrast. So consider the 1D barrier and a height V naught with a with a particle energy E less than the V naught and coming from left and classically particle and reflects completely since the kinetic energy is the insufficient surmount barrier quantum mechanically and particle described by the wave function solving the time independent Schrodinger equation three regions left inside right of the barrier with the continuity zeta and d zeta by the dx boundaries. This yields the reflected wave and a transmitted wave with a non-zero transmissions probability t. Square barrier results dependence for the rectangular barrier Vx equal to the V naught on the 0 less than x less than a and e less than V naught. Wave functions decays exponentially inside the barrier. Now the zeta and zeta tends to the e की power minus kx where the k equal to the under root 2m k equal to under root 2m bracket 1 v naught minus e divided by the h. Matching solution shows the transmission probability. Transmission probability behaves approximately as the t equal to the e की power minus 2ka for sufficient thick or a high barrier. So tunneling is exponential. Tunneling is exponentially suppressed with a barrier height and width but never exactly zero. This explains the phenomena like alpha decay, scanning, tunneling microscopic, and the tunneling diodes. Now, next topic will be the wave functions, coordinate and momentum representation. Wave function quantum mechanics describe the quantum states different bases and position coordinate representation gives the probability density in space while the momentum representation gives momentum space. Coordinate representation wave function zeta x comma t satisfies Schrodinger equation I h dt phi equal to the h cap zeta with the zeta mod of the zeta comma x bracket 1 x comma t to power 2 dx as the probability finding the particle between x and x plus dx position operator x cap zeta x equal to the x zeta x momentum operator p cap zeta x equal to the minus I h dx zeta x expectation values. Now x equal to the integral zeta star x into zeta dx and bracket angular bracket p equal to the integral zeta star bracket 1 minus I h d dx zeta dx. Momentum representation. Define the phi bracket 1 p comma t and equal to the 1 divided by the root 2 yeah, pi h and integral minus infinity to infinity. Now the zeta x comma t e to the power minus I p x by h dx Fourier transform. Then the mod of the phi bracket 1 p comma t square and the dp is the momentum probability density. In the p space, p cap phi p and equal to the p phi p and semicolon x cap and phi p equal to I cap h dp phi p Parseval. Parseval theorem ensures integral mod of the zeta square dx equal to the integral mod of the phi square dp equal to 1. Transformations and the property. Switching basis unitary Fourier transform zeta x equal to the 1 by the root 2 pi h and integral phi p e to power ipx by the h dp. Heisenberg's uncertainty follows delta x delta p greater than equal to the h by the 2 since the narrow phi x and zeta x localized particles require the broad phi p for Gaussian wave packet. Minimum uncertainty holds both the representatives both representation equivalent choice depends on the problems. Example: position for the barriers and momentum for the free propagations. Now, next topic will be the commutators and Heisenberg uncertainty principle. Commutators quantify non-commutativity quantum operators leading directly to the Heisenberg uncertainty principle. Incompatible observables. Commutator definitions. Now the for the operator a cap dot b cap commutator angular bracket a cap b cap equal to the a cap and b cap minus b cap a cap. Key properties bracket 1 a cap b cap equal to the minus bracket 1 b cap a cap. Now bracket 1 a cap comma c b cap equal to the c bracket 1 a cap b cap c scalar bracket 1 a cap b cap plus c cap. Now the equal to the bracket 1 a cap b cap plus a cap c cap. Leibniz rules bracket 1 a cap b cap c cap equal to the a cap b cap bracket 1 c plus b bracket 1 a cap c cap. Canonical will be the bracket 1 x cap comma b p cap equal to the ih and comma x cap and equal to the p cap equal to the 0. Uncertainty principle derivation for the state zeta variance and del a equal to the under root a cap minus bracket 1 a square and Cauchy-Schwarz on operators give the delta a delta b greater than equal to the 1 by 2 mod a cap b cap. Proof is case define delta a cap equal to the a cap minus of the a cap then the bracket 1 delta a cap plus I lambda b cap k power of the 2 greater than equal to the 0 for the real lambda minimized to the bound. For position momentum delta x into delta p x greater than equal to the h by the 2. Consequences. Now the commuting operators a cap b cap equal to the zeros and share the eigenbasis simultaneous eigenvalues. Non-zero commutator implies the no common eigenstates enforcing the uncertainties. Precise x blurs the p angular momentum lx and ly and equal to ihl z and cyclic. So delta Lx and delta Ly greater than the H and Lz by the 2 underpins wave particles duality and the measurement limits. Our next topic will be the Direct notation for state vectors. Direct notation, bracket notation represents the quantum states and operators abstractly as the vectors. Vectors in the Hilbert space independent any specific basis. Kate's brass quantum state. Quantum state is a Kate mod phi column vector in a some basis. The dual bra is the mod of the phi bracket 1 row vector and complex conjugate transpose inner product mod phi and zeta complex variables probability phi zeta square normalization zeta zeta equal to the 1 orthonormal basis n slash m and del equal to delta nm. The operators and expectation. Operators A angular act as the Katz A cap mod zeta expectation A cap and angular zeta x A and zeta eigenstates A cap an with am equal to delta mn. Expansion and the projections. Any state zeta summation n cn n and cn n zeta continuous basis position zeta of the x and x zeta integral x and x dx equal to the 1 cap. Change the basis by the completeness. Key rules linearity phi c1 zeta 1 plus c2 zeta 2 c1 star phi and zeta 1 and plus c2 star phi zeta 2. Other product will be the zeta and the phi is projected tensor product for composites. Now the phi zeta phi and equal to the mod of the zeta and phi. This notation simplifies the quantum algebra uncertainty relation direct originals derivations. Now let's next topic will be the motion in the central potential orbital angular momentum algebra spin addition of the angular momentum in the central potential. In the central potential, motion separates into the radial and the angular parts, with the orbital angular momentum conserved. Quantum angular momentum include the spin, obeys the common algebra, aided by the specific rules. Motion in the central potential for the particle Vr and the Hamiltonian H equal to the Hamiltonian H equal to the p square divided by 2m plus Vr, which is rotationally symmetric. So bracket 1 h comma L equal to the 0 orbital angular momentum L equal to the r cross p is conserved. Quantum mechanics Schrodinger equation separate spherical coordinates eigenstates labeled n L m where L m come from orbital angular momentum. Orbital angular momentum algebra. Orbital angular momentum separators satisfies bracket 1 Lij equal to IH zeta Izk Lk L square equal to the Lx square plus Ly square plus Lz square. Eigenvalues are the L square equal to bracket 1 L comma m equal to h square L bracket 1 L plus 1 L comma m. Lz and L comma m equal to the hm L comma m. L equal to the 0 1 2 m and equal to the minus L to the L. Ladder operators L plus minus Lx plus minus ILy. Now raises lower m L plus minus Lam equal to the h under root L bracket 1 L plus 1 minus m bracket 1 m plus minus 1 and mod L m plus minus 1. So spin angular momentum. Spin yes is intrinsic, not orbital, but obeys the same algebra. Angular bracket yes I yes j I h zeta I j k s k and s square yes ms h square yes bracket 1 s plus 1 and further yes comma ms and yes z and yes comma ms h ms and yes ms For spin minus 1 by 2 and yes 1 by 2 ms plus minus 1 by 2 component are SI h by 2 and the sigma I in terms of the Pauli matrix spin couples to the central potential by the spin orbit terms L dot S atomic structure addition angular momenta. Given the two angular momenta J1, J2 and orbital or spin total J equal to J1 plus J2 with the same algebra. If they have the quantum numbers J1, J2, J total J takes the value J equal to J1, J2, J1 plus J2 minus 1 and comma mod J1, J1 minus J2. Each J has the 2J plus 1 values of the yum from the minus j to the plus j. Product basis j1 m1 j2 m2 related to the coupled basis and mod j comma m. So by the Celebes Gordon coefficient example 2 is spin minus 1 by 2 combined to a triplet yes equal to the 1 singlet yes equal to the 0. Hydrogen atom. Now let's deal hydrogen atom. Oh, it is a trending topic. Hydrogen atom bound state electron Coulomb potential proton solved exactly by the Schrodinger equation labeled by the quantum numbers n, l, m. Schrodinger equation energy is proton electron center mass frame electron moves Vr equal to the minus e की power 2 divided by the 4 pi epsilon naught r giving the time independent Schrodinger equation bracket 1 minus h square divided by the 2 mu bracket 2 mu and Laplace square minus e की power 2 divided by the 4 pi epsilon naught r bracket 1 zeta equal to the e and zeta and with the reduced mass mu separation spherical coordinates yields the discrete bound energies. So En equal to the 13.6 electron volt by n square n equal to the 1 2 3 independent LM Coulomb Coulomb degeneracy quantum numbers and orbitals. Now solution factor into the radial and angular parts zeta n lm r theta phi r equal to r nl bracket 1 r and y l m theta phi. YLM are spherical harmonics. RNL are the hydrogen radial functions. Quantum numbers n equal to 1 to principal energy side, L equal to 0, n minus 1 orbital angular momentum, m equal to the minus L and Lz projection, Bohr radius and ground state characteristic length in the Bohr radius A naught equal to the 4 pi epsilon naught h square by the mu into the E square 0.529 angstrom. So setting the scale ground state orbital, ground state n equal to the 1 and L equal to the 0, m equal to the 0, spherically symmetric and the maximum probability density r equal to the A naught. Degeneracy and spectroscopy. Each level n has the n की power 2 spatial states and sum over all the Lm becomes the 2 की power 2 into n की power 2 including the spin and transition between the levels produce and hydrogen spectral lines Lehman, Balmer, etc. With the proton energy equal to 13.6 eV and bracket 1 by the nf की power 2 minus 1 by ni की power 2 matching the Bohr formula and atomic spectra. Now, next topic will be the Stern-Gerlach experiment, time independent perturbation theory and application. The Stern and Gerlach experiment shows a space quantization spin time independent perturbation theory gives the systematic formula small corrections energy states when Hamiltonian weakly modified. Stern-Gerlach experiment beam neutral atoms and silver passes through the inhomogeneous magnetic field with a strong gradient along the jet. Each atom has the magnetic moment mu from its unpaired electron spin and force Fz and mu equal mu into the dvz by dz. So atoms with different mu deflected differently. Wow. Beam neutral atom. And now silver passes through the inhomogeneous magnetic field with the strong gradient along the z. Each atom has the magnetic moment mu and it unpaired electron spin and force Fz and mu z dvz by the dz atom with a different mu z deflected differently. Classically, a continuous spread of mu z gives the continuous smear screen. Instead, the beam splits into two distinct spots and corresponding to the mu z plus minus mu b and spin 1 by 2 with S2 Sz and equal to the plus minus H by 2 and this demonstrates that the spin is the intrinsic angular momentum with the discrete projection. A single component example Sz is quantized and measuring it destroyed the information about the component's non-commuting observation. Time independent perturbation theory setup. Consider the Hamiltonian H cap equal to the H naught plus lambda V cap, and where the with the H cap exactly solvable, H naught cap n naught and equal to the E n naught and by the n naught. For a small lambda expand energy and the state En equal to the En ki power 0 plus lambda En ki power 1 and lambda 2 and En ki power 2 and equal to the N0 plus lambda N1 and non-degenerate first order results. Now insert expansions into the H naught cap plus lambda V cap and mod level first order energy shift. First order energy shift En1 equal to the N0 and V cap N0 first order state corrections. Now the N1 equal to summation M not equal to the N and M0 V cap N0 and by the En0 minus En0 and M0. So this shows the shift is just expectation values. The perturbation state mixes with others weighted by off diagonals matrix element energy denominators. Now degenerate a case outline if the several A alpha and 0 share the same E naught, one must first diagonalize B cap. Within the degenerate and subspace, find the good zeroth order combination. The non-degenerate formulas apply those new basis states and typical application is Stark effect hydrogen. Stark effect hydrogen in a weak electric field linear shift for the degenerate level found by the diagonalizing the dipole operator n subspace. J-man effect and splitting atomic levels in the magnetic fields V proportional to the V cap proportional to the L and L dot B or S dot B is spin orbit coupling and fine structure treat relativistic corrections perturbations to the Coulomb Hamiltonian together Stern and Gerlach motivates spin quantized angular momentum time independent perturbation theory then explains how much discrete level shift and mix under the weak external fields. Now, variational methods. Variational method, time-dependent perturbation theory, and the Fermi's golden rules and selection rules. The variational method approximates bound state energy above while the time-dependent perturbation theory gives the transition amplitudes rates with the Fermi Golden's rule and selection rules determining which transition actually occur. Variational principle states that for function zeta expectation values e zeta equal to the zeta h cap zeta by the zeta and zeta. So and satisfies the e zeta greater than equal to the e naught, and where e naught is the exact ground state energy with equality only. If zeta is the true ground state, in practice, choose a parameterized trial zeta and bracket 1 alpha I respective symmetry. Compute the E alpha I minimized with respect to alpha I. This yields an upper band to the E naught by constraining zeta to be orthogonal to the lower state y the parity other symmetrical one, and can bound some excited energy time dependent perturbation theory for h cap t h naught n plus v naught t with the unknown eigenstates and n of the h naught cap expanded states and of zeta t equal to summation n, and now the summation n c n t e to power minus I e n t by the h mod n. So inserting into the Schrodinger equation, keeping only first order V cap gives m is not equal to the n. So Cm dot 1t and equal to the minus I by the h summation n and Cn 0 t e to power I omega men t and v men t and omega men equal to the em minus en divided by the h. So where v men t and equal to the m v cap t and if initially in the I and the first order amplitude for the f is the cf1 and t equal to the minus I by h. Integral 0 to the t and dt ki power 1 and e ki power I omega fi t ki power 1 vfi t dash. So Fermi Golden's rules for a weak nearly harmonic perturbation v cap t v cap e ki power minus I omega t continuum final states f with the density states rho ef transition state from I WIF equal to the 2 pi by h and f v cap I square rho EF evaluated at the energy conservation EF equal to EI plus minus H omega, and this gives the spontaneous induced decay absorption rates used in the atomic, nuclear, and solid state physics. Selection rules. Now the transient element Fv cap I and vanishes if forbidden symmetrics non-zero cases defined. Selections rules. Now typical examples: electric dipole transition with the V cap cross R and E imply delta L plus minus 1 delta M 0 plus minus 1 atom from angular momentum. Parity properties are parity if H naught has the definite parity and V cap is even odd and only states same opposite parity connect. Angular momentum coupling total J must satisfy triangle rules and with a photon spin 1 and delta J equal to the 0 plus minus 1 excluding 0 to 10 to the 0 even transition. Thus the variational method approximate level position time dependent perturbation theory with the Fermi's golden rule. Selection rules predicts allowed transition and their rates. Our next topic will be the identical particles and Pauli exclusion principles and spin statistics connections. Identical quantum particles require the symmetrical many-body wave function fermions, half-integer spin, obey antisymmetric states, Pauli exclusion principles, bosons, integer spin, occupy symmetric states enforced by the spin statistics and connections. Identical particles and symmetry. Identical particles are the indistinguishable even in the principle, so exchanging the labels cannot change the physical predictions, and the many particle wave functions must change at most by the phase under the particle exchange. In nature, only two possibilities occur: symmetric total wave functions unchanged under exchange, boson, integer spin, antisymmetric total wave function, single sign flips under the exchange and fermions half integer spin. Now Pauli exclusion principles. For two identical fermions, antisymmetric condition zeta equal to the 1 to 1 comma and dash dash 2 comma and equal to the minus zeta and 2 1 and implies zeta equal to the 0. All the quantum numbers same, no two identical fermions can occupy same quantum states. Atom, this means no two electrons share same set NL, explaining cell structure, periodic table organization, degeneracy, degeneracy pressure, white dwarf, and neutron stars, spin statistics connection. Spin statistics theorem states that integer spin particles 0, 1, 2 must have symmetric states, follow the Bose-Einstein statistics, photons, helium 4 atoms, half integer spin particles 1 by 2, 3 by 2 must have antisymmetric states, follow the Fermi-Dirac statistics, electron, proton, neutrons, relativistic quantum field theory. This arises demanding Lorentz invariance and positivity energy microcausally using the Bose commuting fields, integer spin, Fermi anti-commuting fields, half integer spin ensures consistency, yields the Pauli principal consequence. Now, to this quantum mechanics finish. Further is the thermodynamics statistical physics. Law of thermodynamics and their consequences. Four laws thermodynamics govern energy, entropy, temperature, physical system, profound consequences, heat engines, universe, evolution, quantum statistics. Zeroth law, thermal equilibrium, defines temperature, system A, B, equilibrium C, with term A and B are in equilibrium with each other, enabling thermometers. Consequence temperature transitive allowing consistent thermodynamic scale. First law energy conservation. Delta U equal to the Q minus W internal energy change equals heat added minus work done per cycle closed integral du equal to 0 implies no net work from the heat without energy input. Consequence perpetual motion machine first kind impossible energy conserved universally. Second law entropy increases Clausius heat cannot flow from cold to the hot spontaneously. Calvin Planck no engine extract the work from single reservoir without waste heat. Entropy ds equal to the dq reversible upon t greater than equal to 0 for isolated system. Consequence time arrow irreversibility heat engine limited by the Carnot efficiency neta equal to the 1 minus Tc upon Th universe trends towards the heat death. And third law is the absolute zero. Entropy approaches constant, often zero, as the t tends to zero. Consequence untenability absolute zero. Low temperature specific heats vanish. Quantum ground states dominates. Example, Nernst theorem. Now next topic will be the thermodynamic potential. Thermodynamic potential, Maxwell relations, chemical potential, phase equilibria, phase space, and micro and macro states. So thermodynamic potential, Legendre transform internal energy, simplify calculation for the specific variable held constant. Maxwell relation links mixed partial derivatives, while the chemical potential and phase equilibria govern the mixtures and transition. Phase space underpins statistical mechanics, and by distinguishing microstates specific configurations from the macrostates observable properties observable properties and thermodynamic potentials. Internal energy U S V N primary Legendre transform yields enthalpy H equal to the U plus PV and natural variable SPN and useful constant pressure. Helmholtz free energy F equal to the U minus Ts Tb and minimizes equilibrium constant Tb and gives free energy equal to the G equal to H minus Ts Tp and minimizes spontaneous processes constant T and P. Differential forms du equal to the TdS minus PdV and plus mu into dn and df equal to the minus s dt minus pdv plus mu dn. Chemical potential mu equal to the dg by the dn t comma p and gives the free energy per particle. Maxwell relations equality mixed particle del square u by del s del b equal to del square u divided by the del v by del s yields. Now dt by the dv at the s entropy constant equal to minus dp by ds v constant ds by dv at the t constant equal to dp by dt v constant. This expresses hard to measure quantities ds by the dv dt and measurable one like the Cp, Cv, alpha and Kt. The chemical potential and a phase equilibria at the equilibrium multi-phase multi-component system mu I alpha mu I beta each species I phase alpha beta for the pure substances and phase transition liquid gas d mu equal to 0 implies the Clapeyron equation dp by dt equal to delta h by the t delta v gives phase rules f equal to c minus p plus 2 degrees of the freedom. Now phase space and the states. Phase space is the 6n dimension space position momenta n particles. Microstate is a point bracket 1 q comma p. A macro state is a coarse grained region with a fixed macroscopic observables energy volume particle number entropy s equal to the k l n omega. Omega is the number of the microstates in the macrostates macrocanonical assemble, and this links thermodynamics to the statistical mechanics. next topic will be the microcanonical. Microcanonical and canonical and grand canonical ensembles and partition function. Microcanonical, canonical, and grand canonical ensembles provide statistical framework system different constraints using partition functions compute thermodynamic averages. The microcanonical ensemble isolated system with a fixed energy E and volume V particle number n, all the accessible microstates phase space volume omega EV and have the equal probability 1 by omega entropy S equal to the K into Ln omega. Ln omega. So temperature from the 1 by T equal to ds by dE partition functions zeta omega itself ideal exact energy conservation but hard for the fluctuation. Canonical ensemble closed system thermal contact with a heat bath at the temperature T and a fixed V and N probability of the microstate with the energy EI and Boltzmann factor PI equal to the e की power minus beta EI by the Z, where the beta equal to the 1 upon the KT and partition function Z equal to summation I and e की power minus beta E. Free energy F equal to the minus K into T log Z. Average like the E equal to the minus del Ln Z by del B. So energy fluctuates delta E approximate under root kt square CV. So grand and the canonical ensemble open system exchanging energy particles with a reservoir the T and a chemical potential mu and a fixed V probability. And a PIN and equal to the e की power minus a beta and EI minus mu n and further with a grand partition functions and that is the zeta n equal to 0 infinity summation I and e की power minus beta and ei minus mu n. Grand potential equal to the minus kt ln e. So average n equal to the kt and delta and by the del u. So both energy and particle number fluctuate, suitable for the dilute gases or adsorption. Equivalence and applications. Large system makes the ensemble equivalent and fluctuations negligible. Micro-canonical for the stars, canonical for the solids, grand canonical for the ideal gases. Z equal to the V divided by the lambda cube की power n divided by the n factorial and e की power 2 V by the lambda cube and with the fugacity and Z equal to the e की power beta mu and all the Yeltsin equation of the state PV equal to the KTN. Then further, now next topic will be the free energy and it's a connection with the thermodynamic quantities. Helmholtz and Gibbs free energies connect statistical mechanics thermodynamics by linking the partition functions to the measurable quantities like the pressure, entropy, spontaneity. Helmholtz free energy defined as F equal to the U minus Ts natural variable Tv and where the differential df equal to the minus s dt minus pdv plus mu dn. In the canonical ensemble, f equal to the minus kt ln z. Z is the partition function key relations. S equal to the minus df by the dt v comma n p equal to the minus df by the dv dn and mu equal to the df by the dn. Dv minimizes at the constant Tv and the delta f less than 0 for spontaneous and the isothermal isochoric process. Gives the free energy G equal to the H minus Ts equal to the U plus PV minus Ts natural variable Tp and Dg equal to the minus S dt plus V dp plus mu into Dn. In the grand canonical ensemble, G equal to the mu n at equilibrium relation S equal to the minus dg by the dt p comma n. So V equal to the dg by the dp t comma n minimize at a constant t comma p delta z Delta G less than 0 predicts the spontaneity, example, chemical reaction, phase transition, applications, and equilibria. So phase coexistence when the G alpha equal to the G beta and chemical equilibrium summation Vi Ui equal to the 0. F suits fixed volume simultaneous G for the constant pressure experiment both yield the Maxwell relation example del S by del V at the t equal to the dP by the dt at the V. Connect to the heat capacity Cv equal to the minus T in bracket 1 d square. Cv equal to minus T bracket 1 d square F by dt square at the V. So further. Now next will be the classical and quantum statistics. Classical statics Maxwell-Boltzmann applies distinguishable particle or the high temperature low density limit. Now while the quantum statistics Bose-Einstein bosons, Fermi-Dirac fermions accounts indistinguishability, quantum effects, Pauli exclusion, Maxwell and the Boltzmann classical statistics. Particles treated distinguishable average occupation numbers n zeta g e to power minus beta bracket 1 zeta minus mu divided by the z1 g degeneracy beta minus 1 by the kt mu chemical potential z1 is the single particle partition function valid when the n bar and less than the 1 dilute limit underlies ideal gas law PV equal to NKT, Bose-Einstein statistics, bosons, integer spin particles, photon, helium-4, symmetric wave function, allow the multiple occupations. Now the n bracket 1 zeta, g divided by e to power beta, zeta minus mu minus 1 and mu less than 0, mu 10 to the 0 for photons. Bose-Einstein condensation below the Tc proportional to the n ki power 2 by 3, n equal to the n by the v. All the excess particles occupy the ground state. Fermi-Dirac statistic fermions, half-integer spin particles, electrons, protons, antisymmetric, and wave functions enforce the Pauli exclusions n less than equal to the 1 occupation n zeta g divided by the e ki power beta bracket 1 zeta minus mu and plus 1 Fermi energy ef at the t equal to the 0 fills the state up to a maximum degeneracy pressure even at the t equal to the 0 comparison table expect and Maxwell and Boltzmann and Bose-Einstein and Fermi-Dirac. So particle distinguishable and classical, indistinguishable bosons, indistinguishable fermions, n bar zeta, e to power minus b, e to power zeta minus mu, and 1 by the e to power beta bracket 1 e to power minus mu, zeta minus mu minus 1 and 1 upon e to power beta e zeta minus mu plus 1. So maximum occupations unlimited 1 per state. Low T behavior, classical gas, condensation, degenerate Fermi gas. Example, ideal gas and high temperature, superfluid, helium 4, BEC, electron gas, and white dwarfs. Now, next topic deal with the uh, ideal boss, and Fermi gases, and principle of the detailed balance. So, ideal boss and Fermi gases are non-interacting quantum gases owing the Bose-Einstein-Fermi-Dirac statistics, while the principle of the detailed balance characterizes microscopic reversibility at equilibrium. Ideal Bose and Fermi gases for the non-interacting gases in the grand canonical ensemble mean occupation of the single particle level of the energy zeta is. So n zeta equal to the 1 upon e to power beta bracket 1 zeta minus mu plus minus 1. So with the minus for the boson, Bose-Einstein, and plus for the fermions, Fermi-Dirac. The ideal Fermi gas electrons in a metal's neutron in the star Pauli-Exclusion limits n bar less than equal to the 1, giving the Fermi C field. Fermi C field up to the Fermi energy EF at the T equal to the 0, pressure at the T equal to the 0 is the degeneracy pressure. Now, ideal Bose gas, cold atoms, photons with the mu equal to the 0, many bosons can occupy the same level below the critical temperature Tc. Macroscopic fraction condenses into the ground state Bose-Einstein condensation. Thermodynamic quantities, pressure, energy, heat capacity come from the grand potential omega equal to the minus kt summation I ln bracket 1 minus plus z e to power minus beta ei with a fugacity z equal to the e to power beta mu. Upper sign fermions, lower bosons. Principles of the detailed balance. Now, the detailed balance requires equilibrium. Every elementary process exactly balanced by its reverse. Transition I to the j, rates Wij equilibrium, probability Pi equivalent, satisfy Pi equivalent Wi to j, Pj equivalent Wj to the I. So, for all I to the j, this condition ensures stationarity. Equilibrium distribution implies the monotonic entropy increase the system, relaxing equilibrium, Boltzmann-Yates theorem. Quantum gases leads to the Bose-Einstein and Fermi-Dirac factors, collision terms. Now, stimulated emissions enhancement the 1 plus n bar bosons, Pauli blocking, and 1 minus n bar for fermions, guaranteeing equilibrium solutions and kinetic equations that matches the grand canonical and distributions above. Now further black body. Now next topic was black body radiations and the Planck distributions law. Black body radiations is the electromagnetic spectrum emitted by an ideal absorber in the thermal equilibrium perfectly described by the Planck's distributions law, which resolved the classical ultraviolet catastrophe, classical failure, Rayleigh-Jeans law. Classical theory treated cavity models and harmonic oscillators with average energy kT. So equipartition energy density per frequency U equal to U bracket 1 the mu comma T equal to the 8 pi mu square divided by CQ KT diverging as the V tends to infinity unphysical catastrophe. Planck's quantum hypothesis. Planck 1900 quantized oscillator energy En equal to nh mu n012 Planck constant average energy by the Boltzmann factor E equal to summation nh mu e to power minus nh mu divided by the kt and for divided by the e and e to power minus nh mu divided by the kt and equal to the h mu divided by the e to power h mu divided by the kt minus 1. Planck's law spectral energy density U bracket 1 V comma T and 8 equal to 8 by h mu cube by c cube and 1 upon e to power h mu and by kt minus 1. wavelength will be the b bracket 1 lambda comma t equal to the 2 hc square by lambda 5 into 1 upon e की power hc by lambda kt minus 1. Peaks at the Wien's law, lambda max T constant, total power Stephen Boltzmann, sigma T की power 4. Consequences low V, low mu equal to the E KT, KT Rayleigh-Jeans limit. High V exponential cutoff, no catastrophe, photons as the bosons, mu equal to 0, matches the Bose-Einstein statistics. Birth of the quantum mechanics, explain cosmic microwave backgrounds. Thus, thermodynamics, statistical, and physics is finished. Now let's deal electronics and experimental methods. Semicon Now next topic deals with the semiconductors. Semiconductor devices, diodes, Johnson's transistors, field effect devices, homo heterojunction devices. Now, semiconductor devices rely on the p-n Johnson's field effects, rectifications, amplification, swift switching with the homo and the heterojunctions, enabling the diverse functionalities from the diodes to the high-speed transistors. Diodes and the p-n junctions as a p-n homojunction forms the depletion region with the built-in potential VVI, allowing forward bias conduction electrons, holes, and recombine but reverse bias and blocking the depletion widens. Rectifies the AC to DC variant Schottky metal semiconductor fast switching genre for the breakdown regulation led emitter light by the recombination bipolar junctions and transistors BJT. NP and NP or PNP structures, two PN junctions, emitter base forward biased injects carriers into the base collector base reverse biased and collects them. Current again beta IC divided by the IB greater than the 100 used for the amplification switching. Field effect transistors FET voltage controlled channel current modulated by the gate field JFET ME JFET MESFET depletion mode gate depletes channels homo metal semiconductor junction MOSFET MOSFET enhancement depletion oxide insulated gate forms MOS capacitor inverting channels, accumulation, depletion, inversions, homo and heterojunction devices. Homo junction, same materials, SIPN, standard diodes, BJT, MOSFET, heterojunctions, different band gaps, GAAS, band offsets, create 2D electrons gas. HBT heterojunction BJT high speed frequency microwave RF HEMT HFET high electron mobility transistor modulation doped heterojunction for greater than the 500 gigahertz operation lasers LED quantum wells heterostructures GAS or ALGAS. The device type, junction, key features, and application. PN diode, HOMO, rectifications, power supplies, BJT, and HOMO, current gain, amplifiers. Now MOSFET, MOS, high density, and IC logic. HBT, hetero, high frequency, RF wireless, HEMT, hetero, high mobility, MM wave. Now let's next will be the device structure, device characteristics, and frequency dependence and applications. Semiconductor devices featured layered structure, p-n junction, gates, hetero interface enabling control carrier flow with the characteristics like the IV curves gain determining performance across the frequency from the DC to the MM waves. Now device structures and characteristics. PN diode, PN homojunction, depletion region, exponential forward IV, I proportional to the e to power V by Vt, reverse leakage blocking structure diffuse ion implanted doping BJT. Now NPN PNP emitter based collector sandwiches high beta equal to IC by the IB and greater than 100 linear amplifications. Now region vertical structures limits scaling MOSFET and the gate oxide channel source drain threshold voltage VTH transconductance GM equal to delta ID by the delta BGS high input impedance planner for ICS HBT heterojunctions emitter based LGAAS and ALGAAS high current gain at the high speed and low base resistance. HEMT, HFET, modulation doped heterojunction ALGAN, GAN forms 2DEG channel, high mobility, low noise, frequency dependence, diodes, BJT, low cutoff, FT, GHZ, transit parasitic limits BJT base transit time tau b proportional to the WB square MOSFET FT 100 gigahertz SI now greater than 1 T hertz LNP gate capacitance charging limits HBT HEMT FT greater than 500 gigahertz LNP HBT greater than the 1 T hertz LNP HEMT hetero barriers reduce the parasitics ideal for the yum wave RF. Application tables. No devices keep characteristic frequency range. Application. PN diode, rectification, DC megahertz, power supply detectors, BJT, high gain, kilohertz, gigahertz, audio, RF, amplifiers, MOSFET, high density speed, DC, terahertz, CPU, logic, power switching, HBT, high speed and gain, gigahertz, MM wave, 5G base station radars, HEMT low noise and the mobility MM wave T-Hertz SATCOM imaging 6G. And now next topic will be oh next topic will be the optoelectronic devices, solar cells, photodetectors, LEDs. Now the optoelectronic devices convert between electrical optical signals using the semiconductor junction with the solar cells generating the power from the light and photodetectors sensing it and the LEDs emitting it. Solar cells PN or Schottky PN or Schottky junctions absorbs photons above the band gap, creating the creating the electron hole pair separated by built in the field and anti reflection coating emitter n type base b type back surface field efficiency p output p in voc JSC, VOC, JSC, FF up to the 25% silicon greater than the 40%, greater than 40% multi-junction GAAS, IV, I minus V, J equal to the JL minus J naught bracket 1 e की power q V divided by KT minus 1 fill factor FF 0.8 applications photovoltaics panels space power photodetectors are the photodiodes. Now reverse biased PN junction photocurrent IPH neta Q phi A neta quantum efficiency phi flux A area PIN structure intrinsic layer minimizes capacitance speed greater than 10 gigahertz responsivities are equal to IPH by the P optimum Q lambda by HC. Avalanche photodiodes APD multiply by the impact ionization gain greater than the 100 applications optical comms fiber imaging CCD CMOS spectroscopy light emitting diodes, forward bias PN junctions, radioactive recombination emit the photons H omega EG, direct band gap material GAAS and INGAN. Essential structure heterojunction quantum well confined carrier light and example GAN and INGAN essential structure heterojunction and quantum wells confined carriers like GAN slash LINGAN, blue, lead, efficiency, internal quantum Ni equal to R red and divided by the R red plus R non-red. So extractions N external and photon escape and power P Ni N exterior IV application displays lighting and greater than 100 IM slash W and a white LED indicators. Comparison device operation key metric material application. Solar cells light to the electric and efficiency 20%, SIGAS and perovskite. Renewables, photodiode light to the current, bandwidth greater than gigahertz, SIIN and GAAS fiber optics, LED, electric light, wall plug, N, neta greater than 50%, GAN, GAASP, illuminations. Now, next topic will be the operational amplifiers and their application. Operational amplifiers OPOA amperes are high gain differential amplifiers with the feedback enabling precise analog signal processing for amplification, filtering, integrations and more. OPAMP ideal. OPAMP ideal characteristics. Differential input. V output A bracket 1 V plus minus V minus A to infinity. Key specs infinite input impedance 0 output impedance infinite bandwidth gain 0 offset input bias current virtual short V plus V minus negative feedback virtual ground inverting input 0 volt basic configuration inverting amplifier V output equal to the minus RF by R in and V in gain G equal to the minus RF divided by the R in virtual ground at the inverting input non-inverting amplifier V output equal to the 1 plus RF divided by RG bracket 1 V in high input impedance, voltage follower, buffer, V output equal to the V input, unity gain, and RF equal to the zero isolate stages. Voltage follower, buffer, V output equal to V in, unity gain, RF zero isolate stages. Integrator and differentiator. Integrator is the V output equal to the minus 1 by RC integral V in dt, and capacitor feedback low pass response aided resistor to prevent saturation, differentiator V output minus RC dV in by dt, capacitor input high pass noise sensitive practical with resistor capacitor resistor. Application table. Application and circuit function key parameters. Inverting ampere. Now RF by R in gain summing G equal to minus RF by R in and bandwidth F minus 3 dB F and T. So comparator open loop. Now the digital threshold hysteresis by the positive feedback. Active filter Sallen key low or the high pass. Q equal to 1 by 3 minus alpha cutoff. FC equal to the 1 divided by 2 pi RC. Instrumentation ampere 3 OP ampere. High CMRR gain G equal to the 1 plus 2 RF by RG. Noise rejection PID controller. Now sum of the PID process control proportional plus integral plus derivative. Voltage regulator. Now error ampere. Stable output feedback stabilizes versus low temperature. Frequency response limitation. Open loop gain the roles of AF equal to the A naught divided by the 1 plus j f by the fp. So unity gain the bandwidth. Ft equal to the a naught fp tends to the 1 to the 100 megahertz sine raw sine slew rate dv out by dt max 1 to 100 v by the mu second limits large signal speeds stability requires the phase margin greater than the 45-degree. Compensation capacitor. Common IC 741 Classic, OP07 Precision, TL081 JFET input, LM358 single supply. Now next topic will be the digital techniques, application, registers, counters, comparators and similar circuits. Digital techniques use the flip-flop building blocks sequential circuits like the registers, data storage, counters, event sequencing, comparators, magnitude comparison, enabling memory, timing, control, processors, logic system, registers, chain of the D flip-flop with a common clock for the parallel or the serial data storage and shifting types shift registers serial in or out and CISO parallel in or out PIPO and universal bidirectional storage register holds the data with the load enables characteristics n bit capacity clocked operations application and data buffering serial parallel and conversion UART. Now counters flip-flop chains that advance the states on the clock edges asynchronous or the ripple or the synchronous. Now a ripple counter asynchronous JK or D flip-flop toggle on the output is modulo 2 to power n synchronous counter clock all the FF simultaneously and get for the decoding up down decade BCD ring Johnson decade reset 10 ring circlets single one, characteristics count, range, modulo, propagation, delay, and application frequency division. Even event counting timers, comparators, and similar circuits. Magnitude comparators compares A equal to the B greater than A using XOR and logic 1 4 bits cascadable. 1 bit A equal to the B and ampersand A uh, B, A greater than B, A B. So priority encoder converts highest active input to the binary 8 to 3. So multiplexes decoder and route select data. Application ALU arithmetic and sorting networks and interrupting the controllers. So application table, circuit key features, speed limit application, register, data storage or shift. Now the clock frequency, CPU register, FIFO, serial comms. Now ripple counter, simple asynchronous proper proc delay and tau, low speed clocks dividers. Sync counter, fast glitch free clock frequency, timers frequency synth. Comparator A equal to B, A greater than B, A less than B, combinational. Now processor ALU control logic encoder parallel to the serial and combinational and keyboards and ADCs. Now built from the TTL or slash CMOS and IC74XX7476FF7485 comparators VHDL Verilog for the FPGAs. Now, next topic will be the AD or DA converters. So, now AD converter digitize analog signal by the sampling, quantization, encoding, and DA converters reconstruct analog from the digital by the weighted samples method, enabling mixed signal systems like the audio sensors. AD converter principles analog input undergoes sampling Nyquist theorem Fs greater than 2f max hold quantization bits determine the steps and SNR 6.02 n plus 1.76 dB binary encoding key types flash parallel comparators fast 10 SGS per second high power 4 to 8 bits SAR successive approximation binary search with the internal DAC 10 to 100 ms per second 8 to 18 bits and low power sigma delta oversampling plus noise shaping high resolution 16 to 24 bits audio slow 10 second to 100 second ks per second pipeline staged sub ADCS medium high speed 10 second 100 second ms per second 10 to 16 bits error quantization noise aperture jitter inl dnl application data acquisition communication imaging da converter principles digital code driver weighted current voltage sources summed analog output often with reconstruction filter and key types now binary weighted resistor ladder fast limited 8 to 10 bits due to the resistor precision R to R ladder matched resistors scalable 16 plus bits good linearity moderate speed sigma delta oversampling feedback high resolution audio video slow current steering array unit current high speed greater than 1 gs per second video dsp error glitch errors, glitch energy, settling time, monotonicity, applications, waveform generations, motor control, audio deck. audio deck comparison table. Comparison table parameter AD converters, DA converters, key matrix ENOB sampling rate, SFDR, settling time, THD plus N, PSRR, speed range, KS upon S, delta summation to the GS upon S flash, MES R22R to the GSS steering resolution 8 to 24 bits, 8 to 20 bits, and power speed, high speeds, high power, high speeds, high power. Applications, sensors, RF, audio, video actuators. Next topic will be the microprocessor or microcontroller basics. Microprocessors, microcontrollers, integrated circuit execute instruction, but microprocessors emphasize CPU cores, while the microcontrollers integrate peripherals for the embedded control. Microprocessor basics. A microprocessor Intel 8086 Cortex A CPU chip ALU register control unit cache requires external RAM, ROM, I/O timers by the buses address data control general purpose high performance gigahertz clock multi-core power hungry complex OS support application PC server smartphones. Microcontroller basics. Microcontroller AVR AT Mega PIC 16 ARM Cortex M integrates CPU, RAM, flash, EEPROM, peripheral, GPIO, ADC, DAC, UART, SPI, I2C, and timers, PWM, interrupts on one chip, single chip solution, real time, embedded task, lower clock, kilohertz, megahertz, optimized power, sleep modes. Application, appliances, sensors, IoT, motor control. Now, aspect microcontroller components, CPU only, CPU plus memory plus peripherals, memory, external, RAM, ROM, on-chip flash, RAM, power side, high power, large board, low power, single chip, cost, complexity, higher, need PCBs, and lower standalone, speed, gigahertz, pipelined, and megahertz real-time, apps, computing, PCS, and embedded washing machines, applications, microprocessor, OS kernels, graphics networking. Now the 86 laptop, now cross 86 laptops. Now microcontroller firmware loops and Arduino for the robotics, STEM 32 drones, hybrid SoC, and Raspberry Pi combine both. Now, next topic will be the data interpretations and analysis, precision and accuracy, error analysis, propagation of the error, and least square fitting. So, data interpretation requires the distinguishing precision, reproducibility, accuracy, truthfulness, quantifying errors, propagating uncertainties, fitting models by the least squares to extract the parameter reliably. The precision versus accuracy. Precision measures the repeatability, small scatter, small scatter, tight error bars. Accuracy measures closeness, to the true value small bias, high precision, low accuracy, systematic error, calibration offset, high accuracy or low precision, random error dominates. Example target shooting, tight grouping, precise but off center, inaccurate. Error analysis. Error analysis, random error, Gaussian statistics characterized by the standard deviation sigma equal to the under root xi minus x bar square, standard error mean sigma x bar equal to sigma by the root n, systematic error, bias instrument methods not reduced by the repetition, total uncertainty, delta x equal to the under root sigma square plus b square, random plus systematic, confidence interval 68 plus 8% plus minus 1 sigma, 95% plus minus 2 sigma. Error propagations, functions fxy variance now adds the quadratically uncorrelated variables df square equal to the df by dx into dx की power 2 plus df by dy की power 2 plus and rule sum del x plus y and equal to the del x square plus del y square. So product quotient relative error added quadrature del xy by dy xy. So equal to under root dx by x square plus dy by the y square. Now power delta x की power n equal to the mod n delta x by x and x की power of n. List square fitting, minimize the chi square chi square summation I omega I bracket 1 yi minus fxi a की power 2 weight wi equal to 1 minus delta y की power 2 for the linear model y equal to the a naught plus a1 x a1 equal to the n summation xi yi minus summation xi summation yi by the n into the summation xi square minus bracket 1 summation xi की power of the 2 equal to the sigma ai square equal to 1 by n minus 2 into summation wi की power minus 1 by summation wi bracket 1 xi minus 2 x bar की power 2 and goodness fit and reduce x v square equal to the 1 v equal to the degrees of the freedom non-linear fits use the iterative minimization 11 works and the mark quadrant and the concept formula idea purpose now precision q equal to the summation under root summation xi minus x bar की power 2 divided by the n minus 1 repeatability now propagation d delta f equal to the summation under root summation bracket 1 delta f divided by the delta xi into the delta xi equal to a square uncertainty derived quantities list square minimize chi square parameter estimation plus errors. Now part A finished. So let's meet tomorrow. Thank you.